Okay. So how is the class handling this part of calculus?
Not well.
Not well?
No, we're not very good at this.
Well, I don't think that's a reflection on your class as much as it is a reflection on the difficulty of the material.
Probably.
Yeah, incidentally, I wasn't sure if we were working on SAT today. So here's what I have logged in. I have high degree of difficulty SAT questions, I have basic SAT questions, and I have subject math questions. So might actually be better to do that work online just because my material is pretty good.
Gotcha. Yeah, we can do an online session if you'd like to. Do that.
Yeah. Okay, looks like I got it here. Let me read his instructions. Here's your share of compassion, huh? Oh, good. I'm glad to hear that. That means it'll be easy on me, too. All right. There was just one page with that?
I think. Yes.
Okay. Oh, it's a big one. Okay. What did you want to finish up on the other before we tackle this?
I just wanted to run through it one more time and see if I can.
Talking about Taylor's theorem about the remainder?
Yes. See if I can understand it just a little bit more.
Okay. Let me think if there's anything I can add that would help. Well, I don't know. I feel like as I said, I barely understand it. I'm not sure I totally understand it, but I kind of think I do. If we say that the sine of x is equal to this series, or better yet, let's define it like this. What is it? You have it memorized? It's x minus
x cubed over 3 factorial plus x 5 over 5 factorial and so on.
So this is called x to the 2n minus 1, or is it 2n plus 1?
I don't know that part.
The nth term. All right. This is the Taylor series for this function, calculated in a very specific way, which you know exactly how to do. But nothing says that this series converges to sine x. Because all we know is that if you take the first, second, third, fourth, and nth derivative and evaluate it at 0, that this is what you get. And this proves to be remarkably accurate. But how do we know that when we take the entire infinite series, that it actually converges precisely to sine of x? That's the problem. And the reason that's a problem is this other function. This is not sine of x. This is sine of x only between minus pi over 2 and pi over 2. Everywhere else, it's either 1 or minus 1.
Yes.
If I took this function and I applied Taylor series to it, I would get this exact thing. How could I not get that exact thing? That thing was developed by taking the derivatives only at one point, x equals 0. This point right here. So if I were to take this same function and do exactly figure out the Taylor series for this function, I would get this same series. So the fact that sine x is equal to this series doesn't mean that this series converges to sine x. Because this series down here most definitely does not converge to sine x. And yet it's the same infinite sum. So what gives? Why the difference? Well, here's my understanding of it. If we can show that the remainder, in other words, whenever you approximate sine x with a series, you usually approximate it with a certain number of terms, and everything else, the rest of the infinite series, is the remainder.
Right.
So if you can prove that that remainder goes to 0 for some f of z, I believe, then that proves that sine x, or this series, converges to sine x.
Okay.
For this series and sine x, if I go through Taylor's theorem, his analysis of the remainder, and I can show that it goes to 0, and I can do that on sine x. I might have to look in the book how to do it, but I can do it. Then that proves that this particular series converges to sine x because the remainder. If I tried to use Taylor's theorem on this other series that I drew, if I tried to apply Taylor's remainder theorem on this series, it would not go to 0. It most likely would go to 1, because it goes to 1 everywhere after pi over 2. So
What about negative 1?
Well, when you look at series, you go with n counting up, so I'm not quite sure the other half of that, but
Okay.
at worst, it's one of these kind of series, right? And we already know that that is a divergent series. In other words, whether it's positive 1 or negative 1, the nth term is not 0. It's either plus 1 or minus 1, which means the remainder for this particular series would not go to 0, and therefore you would not be able to assume that it was the same as sine x.
Okay.
Conceptually, that's my understanding of it.
No, that makes sense.
Now, in terms of doing problems, improving, I'm pretty sure I can prove that sine x and cosine x, those series converge to sine x and cosine x. The one that we were working on when we left was that one.
Right.
And that, to me, seems like we came down to e to the x and what? 2x or 2 to the x or something like that all over a factorial. Right? Isn't this kind of where we left off?
Wait, why would it be 2 to the x?
Well, there's an n in here also. Let's see. Where would the n be? It must be n there. And maybe n here. I don't remember. If you have the notes, maybe you could. But if we're trying to evaluate this as n goes to infinity, I think I said that even though you have the product of two exponentials in the numerator, you have a factorial in the bottom. And the factorial is going to outstrip the numerator eventually for a given x. And therefore, the remainder does go to 0 on this function. And therefore, the series for e to the x does converge to e to the x, and that's the proof of it. Okay. Now, I'm not terribly comfortable with what I told you because I'm not positive that if you take the product of whatever we had in our numerator, I know we had exponential stuff in our numerator and we had factorial stuff in our denominator. And to me, that seemed to indicate that the denominator was going to go, in other words, the whole thing would go to 0.
Okay. I follow that.
Huh?
I follow that.
Okay. Shall we go to the other stuff?
Sure.
I'm afraid if we attempt to do a problem with his, it'll take up not only the rest of our hour, but another hour besides. They are, I don't know. I'm not sure I've tried to do a remainder problem. Following their proof of sine x is hard enough in the book. I don't even think your book has that proof. My other book does have it. All right, calculators can't be used. Okay.
All right.
Let me get my thing up here so that I can have room to write. We don't need our multiple choices. I mean, on calculus, I find it rare that the multiple choice actually helps, only as a confirmation. In other words, once you've worked through the math, I mean, if you come up with something and you see it in the multiple choice, then you feel better. But you have to come up with the answer, right?
If you don't come up with it, you feel worse.
Well, I know, but I mean, having multiple choices doesn't help if you can't come up with a number.
Yeah.
I suppose you could back solve these, but for the moment, let's try to do the math-wise. These might be such that it's a little different than the SAT. We might reach a point when we're preparing for your AP Calc exam that we decide that back solving is a great way to proceed. But for now, let's try to do the math.
Okay.
So if this function is continuous, what has to be true about x squared plus bx and 5 sine pi over 2x?
They have to intersect.
They have to be the same at x equal 5. In other words, if they weren't continuous, let's say that they were something like that, then they wouldn't be the same at this point. So for them to be the same at 5, they have to not only intersect, but they have to be like that.
Okay.
In other words, this is a function, so it has to pass the vertical sine rule. So it's not some crazy function where these things intersect, In other words, we can't really have them do that because then it's no longer a function.
Yeah.
So they have to meet at that point. So in other words, x squared plus bx has to equal 5 sine of pi over 2x when x equal 5. So if we do the math, what do we get?
Get the square root of 5 sine x over 2.
Hold on, we're going to plug in 5 for x into this.
Oh, okay.
Okay?
You get 25 plus 5b equals 5 sine of pi over 2.
Right?
Mm-hmm.
What's the sine of 5 pi over 2?
Square root of 2 over 2.
That's an angle that's greater than the unit circle. It's outside of one unit circle, so if we subtract 2 pi from it, it'll be the same as pi over 2. And the sine of pi over 2 is 0. Excuse me, it's 1. Here's our sine curve.
Oh yeah, I'm sorry, I mixed it up with pi over 4.
Right. So if we subtract 4 pi over 2, which is one unit circle from that, then we get exactly pi over 2.
Mm-hmm.
And that's 1. So we now have 25 plus 5b equals 5 times 1. b equals minus 4.
Okay.
And thank goodness they have that as one of their answers. Now, like I said, theoretically we could back solve that, but you still have to know that the hardest part of this problem is knowing that this has to be equal to this at x equal 5. And so back solving would not really help with that. So you have to know that understanding there. So how do we get the relative maximum?
We find zeros, right?
Well, first of all, we take the derivative. We don't find the zeros of this. In other words, this function might look like this. And so it would have zeros there and there, but that's not really what they're asking about. They're asking about where is that and where is that. And in order to find the maximums of a function, we know that when we take the derivatives, we're looking at slopes, and the slopes at those maximums are always 0. So we take the derivative of the function, we set it equal to 0, and we solve. And that'll tell us where on the x-axis those maximums occur. So what's y prime?
6x minus 3x squared.
Set that equal to 0 and solve it.
So what I just do is 6x is equal to 3x squared?
Well, not really. It's tempting to do that because then it looks like you could divide both sides by x. But you actually lose a solution if you try to solve it like that. The way to solve this is factoring. Always think factoring when solving quadratics.
So
There are times where you can solve quadratics by setting a number on the other side, but most of the time you have to factor.
So factor out 3x. So it would be 3x times 2 minus x.
Now you can set both of those equal to 0 and you have your two zeros. So what are they?
X equals 1. What? I'm so confused.
0 for this one.
And 2.
And 2 for this one. Now, that's what we would expect with a cubic. Is a cubic function usually has two humps like that, which means one of these zeros is not a maximum, it is a minimum. So how do we tell? There's the first derivative test and there's the second derivative test to determine whether something is a maximum or a minimum. Personally, I think the second derivative test is the easiest.
Okay.
What's the second derivative of y?
6 minus 6x.
If the second derivative is positive, it means it's concave up, and that would be a minimum. If the second derivative is negative, it is concave down, which makes it a maximum. So when we plug x equals 0 in for the second derivative, what do we get?
Positive.
Which means it's concave up, that's the minimum. When we plug 2 in, we get negative. That means concave down. Concave down is this situation, that's the maximum. So x equal 2, let's see, when x is equal to 2, what's y? When x is equal to 2, we have 3 times 4 minus 8, so the coordinates are 2, 4. In other words, I have to take the x value that I came up with and go back to the original function, this one right here that I drew, and figure out what y would be. In other words, what is that point right there? I know the x-coordinate is +2 and the y-coordinate is 4. So, C. Can I take that as you understand and we should go on?
Yes.
Okay. I'm going to assume if you don't say anything that you get it, and we don't, in other words, that you'll, yeah, I know you're not shy, so you will say something if you don't get it. Might be worth taking a look at the answers just to see if they're in terms of pi or numbers. In this case, it looks like there's a lot of pi's in there. Okay. If its velocity function is equal to this, not sure why they put print. Oh, its velocity vector is equal to this. Okay. We haven't worked with velocity vectors, I don't think. This looks like a polar coordinate. Let me think about this for a moment. The only function I know that looks like that is a polar function, right? Oh, no, hold on. What does that mean? Since when do we have functions with commas in between them? And the only one I can think of is polar coordinates where you have r comma theta, but the sign of that is going to be a number, not an angle. Let's see. If we draw the vector, I guess what they're saying is there's the t-axis, here's v of t, and at any point in time, this function, the value, in other words, at t, the coordinates on that thing are t squared and sine of pi over t, or pi times t. Have you guys worked with velocity vectors in calculus at all?
I don't know.
I don't think I have. So he may be getting this sample examination and not realizing that there's some questions on here that you guys haven't covered. Whether this would be on, this might be on the AP Calc, but I suspect this is from Chapter 10.
Okay.
Okay, so for the time being, let's pass on this and go to the next one, since I have no clue as to how to do it.
Sounds good to me.
And I will take note of it and see if I can figure out how to do it before we meet again. For what value of x does that curve have horizontal tangent lines? Okay. How do we figure out where it has horizontal tangent lines?
Don't we take the derivative?
And set it equal to 0.
But there's a
So
y in
how
it.
do we take the derivative of this?
Do we do it where you take the derivative of both?
Let's take it implicitly.
Yeah, that one.
In other words, we could take it explicitly, but notice that if we solve this for y, we're going to have plus or minus square root. And that's going to be pretty hard to take the derivative of, not to mention handling the plus or minus aspect of it.
Right.
So let's just take it implicitly. How do we implicitly differentiate that?
So wouldn't it be 2y dy dx?
I will call that y prime, okay?
2y prime. Okay.
Just because it's easier to write.
Minus 3y squared y?
3
3x squared? X
And I don't need to write dx dx. That's what I would write, would be dx dx, but that's 1. So it's only when I come across a variable different than x that I need to follow it with either a dy dx or a dr dx or whatever the variable is.
Okay. So minus 30x equals 0.
Now let's solve for y prime. Go ahead.
Wouldn't it be 3x squared plus 30x over 2y?
And we're going to set that equal to 0 because that's where the tangent lines will be horizontal. What makes that function equal to 0?
If y is 0, if x...
Only if the numerator is equal to 0. Doesn't matter what y is, as long as y is not 0.
Yeah.
But we don't care what y is. In other words, we can solve this by solving this. Have we solved that? Same as we did in
Factor out the x.
yeah, factor out 3x. So what are the two places?
0 and -10.
And here we don't care whether it's a minimum or a maximum. One of them is probably a minimum, one of them is probably a maximum, but they only ask about the horizontal tangent lines. D, 0 and -10. What's the answer on 5?
Whoa. What?
Only one thing you need to be looking at. Ignore everything but the largest degree polynomial. Where is it?
It's to the 5th over to the 6th.
It's to the 6th, so it's in the denominator.
Yeah.
So where does this thing go as x goes to infinity?
0.
Uh-huh. If it was in the numerator, if it was x to the 6th over x to the 5th, no matter what the rest of the junk is, it would go to infinity. And if they were equal, it would go to the ratio of their coefficients, which I know you know.
Whoa. I just lost you.
Can you still see my screen?
No. 1 second. Okay, I'm back. Sorry.
Back? Okay, I'm curious as to what it says on my GoToMeeting. Usually it'll say you're offline for a moment if that happens.
I think I accidentally just clicked on something.
Oh, okay. Alright, so what is the limit of this? Well, let's start with the numerator.
We can't have t and x in there, though.
It's true. Notice that the whole thing is by x. X is not part of the integral.
Okay.
Well, the first thing I notice is that x is going to 0. That would mean that if the numerator does not go to 0, this thing's going to go to infinity. However, if the numerator bounces back and forth between 1 and plus, -1 and +1, I don't know what it goes to. How the heck do we integrate that?
I don't think you do. I'm pretty sure you take the derivative of the integral. So it'd just be cosine
Cosine of 1 plus x over x.
Yeah.
Oh, in other words, you're saying that L'Hopital's rule is going to apply here.
Yeah.
Why would it? Because as x goes to 0, now I get it. Notice that as x goes to 0, you're going to take the integral from 1 to 1. And whenever you take the integral from one number to the same number, it's always equal to 0. So we do have a situation where the numerator is going to 0 and the denominator is going to 0. So it qualifies for L'Hopital's rule, although I've never seen it applied like this. So if we take the derivative of both, we get minus sine 1 plus x over 1 plus x. Right? We take the derivative of the bottom, we get 1. So now can we evaluate that as x goes to 0? Yes, we can. That's equal to minus the sine of 1 all over 1, or minus sine of 1, c.
Which is equal to 0.
No, it isn't. 1 is a radian measurement, so minus the sine of 1 radian would be not 0. That's not inverse. Why'd you think c was equal to 0?
Why do I think that sine of 1 was equal to 0?
Yeah.
Because the sine of...
If I look at my sine curve...
Oh, I was thinking like pi. Never mind. I'm sorry.
Sine of 0 equals 0, sine of pi equals 0, sine of 2 pi equals 0. But
Yeah,
sine
right.
of 1 would be somewhere in there, so it would be equal to right there, minus that. But that was still very clever to figure out that we were looking at L'Hopital's rule. I didn't see it when I first looked at it. The only reason I see it now is because I can see that as x goes to 0, you have your limits of integration approaching each other, so the whole thing must go to 0. All right, this looks like a straightforward one.
So I have to find f prime of x and then what it is at 0?
Uh-huh.
So that's going to be 1/2 times 4 sine x plus 2 to the negative 1/2.
Times
Cosine?
the derivative of the inside. You just took the derivative of the outside, but we have to apply the chain rule.
So
And
that'd be cosine. How come it's 4?
because this coefficient.
Okay.
And the derivative of the 2 part is 0. So the derivative of the inside is 4 cosine x.
Okay.
Okay? And now we have to evaluate that. That's f prime of
So
x.
it's going to be 1/2.
So f prime of 0 would equal...
It'd be 1/2 to the negative 1/2 times 4. Right?
Mm-hmm. Let's see, what does that simplify to? That's 1 over 2 root 2 times 4, which is 2 over root 2, which is 2 root 2 over 2, which is root 2. Did I do that right? I think so. E? Do you have answers on these?
No, I don't.
Okay. Well, as long as we find it in there, I guess we should go on. You might want to take notes so you can check if you do come up with answers. I mean, I think I'm doing them right, but I could always be making a math error or something.
No, I'm taking notes on all of them.
Okay, good. I don't like the answer already. Knots?
Oh, that's just the units.
I know. If t is measured in hours and f prime of t is measured in knots. Okay. And knots are nautical miles per hour. Okay, I guess that's the same as saying t is measured in hours and f prime of t is measured in velocity, miles per hour. Then equals what?
Don't you
What's
take
what's the integral of the derivative? Yeah.
So it's just f of t.
Actually, this is the part 2 of the fundamental theorem of calculus. It's f of 2 minus f of 0. And I use the capital F to be the antiderivative of this function. Well, actually, I guess in this case it really is little f, isn't it? Yeah. Because we're taking the integral of the derivative of little f. So it would be that. And do we know what that is? F of 2 minus f of 0. And it's... what is it? What are the units on it?
Knots, I think.
Yeah, if you integrate knots, in other words, if I was integrating miles per hour, I would get miles, right?
Right.
So I have to get miles, or nautical miles. So D would give you the integral as net change. In other words, I'm integrating a rate, and therefore I'm going to get the total nautical miles that were traveled from 0 to 2 hours. In the same way that if you integrated a velocity function, you would get the total miles driven. Anytime you're integrating a rate, you're going to get the original function's units. I like these. These are fun. I hope this is... I haven't had a chance to really look at my book yet. I rented it from the library, so I'm going to have to get it digitized before a couple of weeks, but let's see. Let's cover that. All right, this is pretty straightforward. Equation of tangent line means we're going to need to do what?
Take the derivative.
How are we going to do it? Explicitly or implicitly?
Implicitly.
And we know we can do that because they're giving us both points. They're giving us the x and the y coordinate, which means even if I come up with a y prime that is a function of x and y, I'm going to be just fine because I have both the x and the y point. Okay. So what is it?
2x plus 2y, y prime equals 0. And then solve for y prime. Which is going to be negative 2x over 2y.
So what is the slope of our tangent line at that point?
Negative x over y.
So what is it?
1?
Here's our point. Our point is 5 comma minus 12.
Oh. Oh, it's going to be 5/12.
Okay, so our slope is 5/12. What's the equation of the tangent line general formula?
Y equals mx plus b.
So we have y equal 5/12 x plus b. And how can we solve for b?
Plug in values for y and x.
Plug in this point value.
Yeah.
In other words, minus 12 for y equals 5/12 times 5 plus b. Solving for b, I believe you get 13/12 equals b.
So then it'd be y equals 5/12 x plus 13/12.
Okay. Good to know that we're not in standard format, and they are. So how do I get my answer in standard format?
You need to get the x over on the other side.
And notice they have no fractions.
Ew.
So I have to multiply everything by 12.
Yep.
So,
Negative 5x minus.
so I have 12y equals 5x plus 13. I think it's... Where did I miss the square here? Why is it 13 squared? I don't see my answer on there. I get 12y minus 5x equals 13. Or 5x minus 12y equals minus 13. What the heck? This is an easy problem. What did I do? Did I get the wrong derivative? Y prime is equal to minus 2x divided by 2y. So y prime is equal to x over y, which in this case is minus 5 over minus 12. 5/12 is the slope of that tangent line. So there's the equation, 5/12 x plus b. Plugged in minus 12 for y. I plugged in 5 for x. I get 25/12. Oh, I see what I did. I tried to be too fast. This is minus 144/12. And when I have to actually subtract 25/12 from that, so I get 169/12. Now when I multiply everything by 12, I get 169 instead of 13.
Wait. So
No.
b is equal to 169?
Hold on. Yeah, let me go back. Let's see. I had 144/12 subtracting 25/12. So b is equal to minus 169/12. So yes. So here's our equation. Minus 169/12. And now when we multiply everything by 12, we get that. And that is the same as answer C.
So 5x minus 12y equals 169.
Yeah, when you put it back into standard format, that's what you get.
Got it.
Okay.
the speed is the greatest at speed, wouldn't it be?
Figure above shows the graph of the velocity of a moving object. So that velocity would be pretty fast, right?
Yeah.
That's the highest velocity. What's the highest speed? D.
Gotcha.
Because D is the greatest negative velocity. D is further away from the time axis than B is. So even though it's a negative velocity, its absolute value, which is speed, is greater than it is at B.
Right.
Yeah, really. Hold on, let's look at this. We can probably figure this out. We haven't actually talked about this yet. This is interval of convergence. This is the next thing you're going to get to in this chapter.
Joy.
In other words, when we say sine x equals the sum or equals x minus x cubed over 3 factorial dot 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 dot, we're saying that for all x on the number line, that is true. It doesn't matter if x is 0 or x is infinity or x is minus infinity. This relationship holds true. That's what makes this function so amazing. Because for most functions, it's not true. If I said the following, let's take an easy example. It's supposed to be an n. For what values of x does this series converge?
I don't know.
This is a geometric series.
Oh, so whenever, for less than 1.
When the absolute value is less than 1. Not less than or equal, but less than. And it can be negative, it doesn't matter, as long as it's less than 1. So, the question is, it sure looks to me like if x was greater than 1, this series would not converge. Ignoring this part of it for the moment. In other words, I'm tempted to answer, wow, they don't have my answer on there. I would say, if this was not a less than or equal, I would have picked that. Oh, I see why. Oh, yes. Wow, this is really getting into stuff we haven't had. Maybe we should put this question on. Yeah, this is cool stuff, but it's complicated stuff. You have an interval of convergence, but sometimes you have convergence at one side of the end of the interval and not convergence at the other. In other words, it's possible to have an interval of convergence that looks like this. Most intervals of convergence, incidentally, involving x and x alone are between -1 and 1 because it's a geometric series.
Okay.
If I said, what's this series, interval of convergence, well, you would say x minus 1 has to be less than 1. Right? Whatever's in the parentheses. The interval of convergence for this series would still be from -1 to 1. However, let me change it here for a moment. Might as well talk about this stuff. You're going to get it in class. And if I put this series down, well, now I know that x over 2 has to be less than 1, which means x actually has to be less than 2. And this interval of convergence goes from 0 to 2. But determining an interval of convergence, there's two things. There's the interval of convergence, and then there is the convergence interval, actually. The first thing you discover is the interval that it converges on, but the actual interval of convergence has to have the proper signs on it. In other words, you can have three situations. You can have that one, you can have that one, you can have parentheses and brackets, or you can have brackets and brackets. So you can have four types of endpoint convergence. Now, the question becomes, what is the effect of having this other stuff in here? And in other words, as n goes up, and you see why they started this series at n equals 2?
Yeah.
It would not be defined at n equal 1. Since the log of 1 is 0, we would be dividing by 0. So this is a perfect situation where you have to start a series at something other than 0 or 1. Whenever you're dividing by natural log of n, that's the case. So let's think what happens to the bottom. The bottom rises, but not as fast as n does. The interval of convergence on this thing has to be from, the convergent interval has to be from -1 to 1. So the question is it B, or is it D, or is it even E? Well, the way we discover it is if we substitute -1 for x. Does this series converge? And then we go back and substitute 1 for x. And does it converge? And the way we determine whether it converges, if we substitute -1 for x, then what kind of series do we have? We have -1 to the n times -1 to the n over natural log of n. And this would appear to be -1 to the 2n. Same base, different exponents. I add the exponents. And does this series diverge or converge? The numerator is always 1.
So it diverges?
Yes. The denominator eventually goes to infinity as n goes to infinity. In other words, you'd want to figure out what the nth term was. And the nth term is going to be 1. The numerator is always going to be 1, so the natural log of infinity, that goes to 0. So it's divergent at the left endpoint. So the left endpoint is a parentheses. Does that narrow our choice down? It does kind of look like it does, doesn't it? It has to be D. But just for exercise sake, let's try the right endpoint, which is +1. Well, now that might be a convergent series, because that is an alternating series. And remember what I said about alternating series? You only have to prove that the nth term goes to 0, which this does, And you have to prove that the nth plus 1 term is less than the nth term. Well, what is the nth plus 1 term here? Minus 1 to the, well, and we don't consider the minus 1 to the n. In other words, a sub n is 1 over natural log of n here. It's not this. That's an important thing to realize. When you do this test here, you leave out the minus 1. You leave out the part that makes it alternating. So, in other words, is it true that the natural log of n plus 1 is always less than 1 over the natural log of n? And yes, this denominator is always bigger than that, which makes this fraction smaller than that. So, at the right-hand endpoint, it converges. So here's our interval of convergence, like that. And that matches D. That's actually a good problem. I like that problem. Well, that's a problem we'll be doing next Sunday after you get to that chapter.
Joy.
I'm actually going to, well, I'm kind of curious as how long your teacher is going to spend on Chapter 9, because as I said, one can spend a long, long time on it. I spent a year on it, doing 1 hour a week.
All right, let's do this one, and then I need to go.
Oh, we're beyond time. This one's not a simple one. This one is an inverse trig answer, as you can see by the answers, and it's going to take us a while to go through that. We haven't done that. We haven't done integrals of inverse trig functions yet.
Okay.
So let's make a note that we left off on 12 here.
Okay.
Sorry, I lost track of the time.
Oh, no, you're fine.
Okay, Emily. Do you still want your Friday session?
I do.
Okay, I'll see you.
I'll text you or call you, because you said that online is better, so I can see if there's an online session too.
If you want me to make it online, I can do it right now. You want it online at 3?
Sure.
Let's do it.
Okay, thank you very much.
Sure. I will text you the meeting ID number at 3 on Friday.
Perfect. Thank
All
you.
right. Bye-bye.
Bye.